Hello, Uggies Worldwide. I'm Dave Casler, amateur radio call sign KE0OG, here with another episode of Ask Dave. Our question today comes from Dean Hedstrom, KB0GOH/AG. Now, what that means is he just got his general upgrade, but it hasn't showed up on the FCC website yet. So congratulations to you, Dean, and welcome to being a general class amateur radio operator. That's cool. Okay, he says, Dave, I greatly appreciate your video presentations to help me pass the extra exam. So that's clearly what he's working on next. He wants to add /AE onto the end of his license there. Okay, he says, Dave, greatly appreciate your videos. On page 432 of the 13th manual, figure 428 does not resonate with me. Figure A, series reactance, and he goes off into a bunch of calculations, and he says, because he gets a different answer from what's in the book, he says, am I missing something? The answer is, unfortunately, yes, you are missing something. Let's see if we can try to explain it. Now, think for a minute. Ohm's law, circuit theory, resistors, capacitors, inductors, all of these kinds of things in circuits obey some fairly straightforward laws. But once you jump off the page and get into the air, we're now talking electromagnetic field theory. Okay, Ohm's law is a special case of electromagnetic field theory because what you've done here, the thing that you got wrong, was you were adding an inductive reactance and a capacitive reactance together, which in fact are opposite each other. Let's look at the whiteboard for a minute, and then we'll look at the actual thing in the book, and I'll show you where the secret is, okay? Okay, so the circuit we're looking at is, let's just take the simple case, a resistor, a capacitor, and an inductor. Okay, they're in series. This is R. This has a value of C. This has a value of L. Okay, now the capacitive is 2 pi f C is X sub C. This is the reactance of a capacitor of value C farads. Okay, 2 pi f C. For you engineers out there, this part right here is omega. That's not a W, that's Greek letter omega. Now, X sub L equals 1 over 2 pi f C. L. Okay? Now, resonance is defined as when the reactance X sub C is equal to the reactance X sub L. So we get 2 pi f C equals 1 over 2 pi f L when they're equal, okay? Well, now we can start playing algebraic games and things like that. And when these two reactances are equal, we get 4 pi squared times the frequency squared. Okay, LC equals 1. Well, that's a little hard to deal with. Let's take the square root of both sides. And so, I'm sorry, this should be, oh yeah, it's 4 pi squared. So this one is equal to 1. We want to solve this for the frequency. So F squared equals 1 over 4 pi squared LC. Or, we'll just take the square root of that. F equals 1 over, let's see, the square root of 4 is 2, the square root of pi squared is pi, and then we have the square root of LC. Okay, so this is our basic formula for resonance. Remember, the condition for resonance is when the reactance of the capacitor equals the reactance of the inductor. Okay? And that's the frequency at which it happens. And you can figure that out. Notice that the L is the inductance that is the inherent inductance in an inductor that has nothing to do with frequency. And C is the capacitance in farads that's inherent in the capacitor that has no reference to frequency. However, the reactance is a function both of the capacitance and the frequency. All right? That's the important thing to remember. So now let's go back. Well, I want to show you something else here. When you've all seen this is the so-called real line. Okay, and we'll mark this as 0, 1, 2, -1, -2, and so on. Okay, these are integer values on the real, sometimes just marked RE, line. Now, this could be a resistance. If we had a resistance of 1 ohm, we'd be right there. But where do we put the capacitance? Okay, capacitance takes energy from the circuit and then gives it back. An inductor takes energy from the circuit and then gives it back. Neither of them, and I'm talking ideal capacitors and inductors here, neither of them create any heat, so there's no energy loss. So how do we deal with these? The answer is that we create a second axis right here, and we call this the imaginary axis because the numbers are imaginary. This number right here, 1, and here is -1, okay? So what we end up, if we have a capacitive reactance of 1 ohm and a resistance of 1 ohm, we mark them both out here and draw an arrow. And this is 45 degrees. And this gives us our combined resistance and reactance. Now, in the case of resonance, in this case, we have a capacitive reactance and an inductive reactance that are equal. So if we have this resistance here, how do we draw that line? Well, this cancels this. We draw it this way. It's just resistive, just resistive. And that's where things get interesting, okay? So let's take a look at the actual piece of paper that we're dealing with here, okay? This is the current extra class manual, okay? Current as of 2026. And this is the question: how is the Q of an RLC parallel resonant circuit calculated? Resistance divided by the reactance of either the inductance or capacitance. They're equal, right? Because we're resonant. They are equal. So if you look down here at this diagram, which is the one that you found confusing, please note that we've got a resistance here of 100 ohms. We've got a reactance of 1,000 ohms, and this reactance has to be 1,000 ohms too. Why? Because this circuit is given to us as resonance. So this will equal that in magnitude, not in direction. Because the X sub L points down, the X sub C points up. They're opposite each other. That adds to 0 reactance, which makes this circuit resonant, but we see the values there pop up again. Okay, now let's look at the overlap of the pages here. Okay. In a resonant RLC circuit, that's these two. This one's series, this one is parallel. For a series circuit, increasing R represents increasing losses, right here, and lowers Q. Q, for an inductor or a capacitor, Q is the reactance divided by the resistance. Now, what reactance is that? That's the key. What reactance do you put there? You put the reactance. It doesn't matter whether it's capacitive or inductive because they cancel each other. So we can pick either one. We know in the case of resonance that X sub C equals X sub L. Okay? And we use either one. Q is unitless. It doesn't have ohms. Note here, X is in ohms, R is in ohms. The ohms cancel. This is what we call in engineering a scalar. A scalar is a number that has no units. So you can multiply by a scalar, divide by a scalar, and it doesn't affect the units. You take ohms, divide it by a scalar, you still have ohms. Okay? So, in a resonant, the effect of the resistance depends on whether the circuit is parallel, which is this one, or series, which is this one. For a series circuit, increasing R represents increasing losses, and so it will lower Q. Take a look at this equation here for the series. As the R goes up, that makes this figure smaller, right? Because it's the inverse. And the ratio of L and C, okay, the ratio of L and C, this is the actual capacitance and inductance, not X. It's L and C, okay? So Q in series, if you do a little algebra, you'll find out that it's the reactance of either one of these. Remember, they're equal because this is a resonant circuit. It's the reactance of any of the elements divided by the resistance. Okay? As the resistance goes up, the Q goes down. Q is called the quality factor. Okay? And the quality of the circuit, meaning how well it resonates, goes down. If it's in parallel and you increase this resistance, then that means there's less current flowing through here. Okay? So the circuit depends more on just the reactive components. In parallel, now, as you want the R to go up, and the X is whatever it is that works for you, okay, to give you a reactive circuit. The resistance does not enter into the frequency of the reactive circuit. It is just losses in the circuit. X is never a loss. Okay, so as X goes down, if you use smaller values, they've still got to be equal, both capacitance and inductance, then you get a higher Q. Now, the next question, obviously, is what on earth does that matter? Why is that important? And I will tell you why it is important. A high Q circuit has very high selectivity. A low Q circuit has low selectivity. If you have a dipole antenna, it's a resonant circuit, right? But it resonates only at one frequency. And then you start getting your SWR comes up a little bit more on either side of it. And you want to keep this like about 1.5 on either side. If you have a lower Q antenna, you will lower this and it will be good on a wider frequency band. Dipoles are pretty good. They'll cover the whole band except on 80, okay? Where dipoles have too high a Q to cover all of 80 meters. If you increase Q, which is the case when you are using a mag loop antennas have very high Q, which means very narrow bandwidth. Okay? So a high Q circuit only resonates just within a very small range of frequencies. A low Q circuit can be satisfactorily resonant. It's really technically resonant only on one frequency, but you move far away from it and it still works fine. Okay? So there you have it. That's what's going on. And that's what you missed, is that we're dealing with either XL or XC. You just think of it as the resonant value, the X sub L, X sub C, where they are equal. Take that as your X. It can be either that one or that one. And that's where you were running into trouble there. Okay? So, Dean, I got this email from you on April 1st. It's now April 27th. So 3 weeks plus it took to work through the system here. I hope that this is still helpful to you as you are studying for the extra. The thing you need to keep in mind is simply that once you get off the circuit board and away from DC, direct current, okay, things start to operate a little differently because you're operating in the radio frequency domain, which has a real part and an imaginary part. And you're going to be studying about that for your extra exam, because the extra exam will expect you to work out a number of problems that deal with both real and imaginary. Let me tell you where the word imaginary comes from. What is the square root of -1? What number multiplied by itself is -1? There is no real number that can do that. Okay? There's no real number that can do that. let's pretend there's an imaginary number whose square is -1. Just pretend, okay? That's why we call it imaginary, okay? We'll call that imaginary number I. Except for the fact that in electronics, I equals current. So we'll do what all engineers would do. We'll just use the next letter, J. Boy, isn't that creative? I'll tell you what. Okay, so we call it J in electrical engineering. J squared is -1. Now, J is something we imagined it to be, and we can create a graph where we create an imaginary axis, and the 1 means 1J. The 2 means 2J. There's also a -1J, a -2J, and so on. The J is very important in that. In some of our calculations, we'll end up with 2 J's, get J squared, and we can replace J squared with -1, okay? Isn't that going to be fun? You're going to have fun with that in the extra exam. So there you go. There you have it. Until we next meet, good luck with your studying, and 73.